The story goes that at the January 10th, 1930 meeting of the Royal Astronomical Society, after a presentation on the performance of clocks at the Royal Observatory in Greenwich, the Dutch theoretical physicist Vilem De Sitter was asked to update those gathered that day in the heart of London on his research. As he rose, he began speaking on his efforts to square his cosmological model of the universe with the most recent results being published from the Mount Wilson Observatory that showed that the spiral galaxies seen through the world's most powerful telescopes were rushing away from the Milky Way galaxy at speeds that were proportional to their distance from it. This result, building on the work of Vesto Slipher's earlier research on galactic spectroscopy and Edwin Hubble's observations of various standard candles that showed that the galaxies were in fact island universes outside of our own enormous collection of stars, had thrown the astrophysical community into a state of confusion. Since the publication of Einstein's general theory of relativity some 14 years earlier, all of the solutions to the one powerful equation that had emerged from the work had started from the idea that the cosmos was steady and static. And yet, here was evidence that called that fundamental assumption into question. De Sitter's short presentation laid out some of his own efforts, along with his reanalysis of Hubble's latest data, but at its end, the conundrum remained. One of the participants in the session asked if he or his models could explain the data, the orderly and regular moving away from the Milky Way of nearly every other galaxy observed. De Sitter replied, quote, "I'm not sure that I can." He knew that no matter how he tried to modify his model, it failed to account for the latest data. At some point in the ensuing discussion, the world-famous astronomer Arthur Stanley Eddington wondered aloud why there were only two cosmological models, De Sitter's and Einstein's. Weren't there other possible solutions to the equation the great German physicist had developed? In his comments he said, quote, "I suppose that the trouble is that people look for static solutions," end quote. Though he did concede that De Sitter's solution did allow for an expanding universe as long as that universe didn't contain any matter. Indeed, in the Dutchman's mathematics, any mass placed in his equations would immediately begin flying off to the edges of spacetime, though, as Eddington also wryly noted, quote, "But as there isn't any matter in it, that does not matter," end quote. As the conversation in the room progressed, it became clear that there seemed to be no way in which to account for a universe that was dynamic, a space-time that was an active element in a changing cosmos. The best anyone could do was imagine that all things were moving like the planets or the stars, through space-time, trapped in the gravitational wells created by even larger congregations of mass. This was the limit of the thinking in the room. In the words of historian of science Helge Krah, quote, "From the point of view of the cosmologists in the 1920s, a dynamic universe was a concept outside their conceptual framework, something not to be considered, or if it was considered, to be resisted," end quote. Fortunately, not all of the thinkers were in the room on that day. Even as Eddington, De Sitter, and their colleagues mused over how to solve the problem, there was another man, a Belgian Jesuit priest, who had already provided the solution being sought after on that January afternoon. What's most ironic is that Eddington himself had even seen the paper some 3 years earlier, but in the hustle and bustle of scientific life, and, likely, because it fell outside those preconceived notions of what the universe should be, he had forgotten it. Yet, in its pages, was the final piece of the revolution that had begun some 400 years earlier, when Rheticus had left Fromborg with the manuscript of the aged Nicholas Copernicus that overturned millennia of human thought. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 43, An Expanding Universe. As we begin this week's episode, I feel like I need to spend a little time correcting a deficiency in the last show that occurred mostly because we were running long. In my discussion of the evidence to support Einstein's general theory of relativity, I gave quite the short shrift to the story of Arthur Stanley Eddington and the expeditions to observe the solar eclipse of 1919. One of the reasons I started this podcast was not only to talk about the various nuggets of scientific truth we've managed to figure out over the last several millennia, but also to discuss how we figured those nuggets out insofar as I can. My description of that most important of astronomical observations was severely lacking, and so I'd like to remedy the oversight, if I may. So, to remind you of what was going on in Einstein's thinking to set up the observation, the special theory of relativity had shown the equivalence between the mass of an object and an object's energy. Now, light doesn't have what we would normally call a rest mass, say like an electron or a proton does. But what it does have is a certain amount of energy based on its frequency. The higher the frequency, the more energy that it has. According to the special theory of relativity, this energy can be treated as an equivalent mass, something that can be found by taking the energy of the photon and dividing it by the speed of light squared. And that can be used when calculating the attraction of a photon of light by another mass, like the sun. What this means that if you think of the light from a distant star passing near the sun, there are three possible things that could happen. The first could be that special relativity and the way it conceptualizes space and time and the rest of nature is just wrong. If this is true, when light goes near the mass of the sun, its path will not be bent at all, and it means it'll travel in a straight line. What this means is that if there's a star that's given off that light, that's the origin of that light as it were, if that star is observed, it will be observed to be in exactly the same position with respect to the other stars that are further away from the sun when you try to look at that star if it's near the sun, say during a total solar eclipse. If that were to happen, this could be thought of as a full confirmation of the Newtonian picture of physics. The second outcome could be that special relativity was correct, but that general relativity is wrong. In this view, light does have a mass equivalent, and that mass will be attracted to the mass of the sun as predicted by Newton's universal law of gravitation. This expression, of course, says that masses exert forces on each other, and these forces are sort of forces that act at a distance. This attraction will deflect the path of the photons coming from the star a certain amount, thus shifting the position of the star as observed from the Earth by something that's calculable. In the case of a specific star to be observed in the 1919 eclipse, that amount would be about 0.87 seconds of arc, a small but easily measurable amount given the equipment of the day. If this had been what Eddington's expeditions had observed, that would have meant that special relativity had been confirmed by the observation, but that Newton's description of gravitation was correct, and Einstein's characterization of it arising from a curved or warped space-time as described by the general theory would have been wrong. The third option was that the mass of the sun warped space-time in its vicinity. This warping of the fabric of space-time would cause the path of light to be bent as it traveled through this path of least action that kind of went through the depression or the warp, if we refer to our two-dimensional example from last time, that's created by the mass of the sun. Once again, this bending could be calculated from Einstein's equation, and the change in the star's perceived position could be predicted. This number was double that of the second case and came out to be about 1.75 seconds of arc. Of course, the fourth and final option was that something else entirely might take place, meaning that the physics was not really well understood, but Given Einstein's success in predicting the precession of the orbit of Mercury's point of perihelion, this seemed pretty unlikely. Now, as we mentioned in the last episode, Einstein's first presentation of the full general theory occurred at a seminar at the University of Berlin right at the end of 1915, where he presented his deviation of Mercury's orbit to his colleagues there. In this, he narrowly beat David Hilbert at Göttingen in arriving at this result. The papers laying out the full mathematics were published in early 1916, and with them, the suggestion that the theoretical framework could be tested using a solar eclipse, an idea Einstein had come up with a bit earlier and had even corresponded with George Ellery Hale about in 1912. The story of the three astronomers sent to the Crimea in 1914, just as the Great War was breaking out, was an attempt to make just such an observation, though it should be noted that at the time, Einstein's still incomplete and incorrect work was predicting a deflection number identical to the case where special relativity only was correct. It wasn't until his 6-week period of intense work after the lectures in Göttingen and his facing the problems he had with rotating frames of reference that Einstein would sort out the general theory's last knots and arrive at his prediction that the deflection should be double the result taken from special relativity. Of course, it was the Great War itself that impeded the attempts to make the observations. With the nations of Europe locked in a seemingly mortal battle, any attempts to mount an expedition by the well-funded astronomical institutions there was severely hampered, especially for those institutions on the European continent where travel was severely restricted. The first chance to test the new theory would have actually been on February 3rd of 1916, but this came too soon on the heels of the publications to actually be practical, especially as the path of totality was mostly over the ocean. The next good chance was on June 8th of 1918, where the total eclipse was visible from many parts of the United States in a path that was almost identical to this most recent eclipse of 2017. The United States Naval Observatory sent a team led by John C. Hammond to Baker City, Oregon, near the Idaho border, in the high desert region of that Intermountain West. The location was determined to be the place with the lowest chance of clouds that might obscure the observations, but, as luck might have it, as totality began, a thin layer of clouds did move in front of the Sun-Moon combination. While the team did manage to make a number of observations, their attempts to photograph the positions of the stars near the Sun were unsuccessful. Similar difficulties were encountered by other observing teams across the United States, and so, at those locations as well, no data was taken. An interesting addendum, however, to this part of our story is that the Lick Observatory had also sent a team to get observations of the eclipse from a different location. Unlike most of those other efforts, the pair from Lick, which consisted of W. W. Campbell, the observatory's director at the time, and Heber Curtis, managed to get images of the star fields around the Sun. The problem was that their equipment was stuff cobbled together from spare parts and throwaways at the observatory. You see, Campbell had been invited to Germany to join the University of Berlin's team in trying to catch the 1914 eclipse. He had set up his top-of-the-line equipment in Kiev in the Ukraine, but the outbreak of the war had thrown a wrench into his plans as it had with the others. While he hadn't been arrested, Campbell's equipment had been confiscated, and by the time of the 1918 eclipse, hadn't been returned or replaced by the then Russian and now Soviet government. Nevertheless, the pair did persist and did get images, but these images were of questionable quality. When Heber set out to measure the shift in star positions, he came up with nothing, seemingly disproving all of Einstein's work. Campbell, however, feared announcing these results, suspecting that it was the poor equipment that was responsible for the outcome, rather than actual, real physical sorts of things. The next chance was recognized to be the May 19th, 1919 eclipse, and the British astronomical community was determined to see if they could be successful where the Americans had failed. The person designated to lead the expedition was the former Cambridge professor, now Greenwich Royal Observatory assistant director, astrophysicist Arthur Eddington, who, as a conscientious objector, had managed to keep from being sent to the trenches of France. One of the big reasons for this was that his colleagues convinced the War Board that his upcoming contribution to the eclipse expeditions would be irreplaceable, and so, on those grounds, more than his views on warfare, he was exempted from service. Throughout 1918, Eddington planned and made the final initial observations of the region of the sky where the sun would be later that next year. With the end of the war in 1918, a number of other nations also prepared teams to make similar observations at a variety of locations across the globe, including another expedition from the United States and a team from Australia. What made this eclipse particularly good was that, due to the moon's relative closeness to the Earth being at the perigee point in its orbit, the duration of totality would be over 6 minutes. What made things more difficult, however, was that it began in Africa, traveled across the Atlantic, and then continued on to Brazil. As such, Eddington organized 2 observing teams, one on the island of Principe and the other in Sobral in the South American nation of Brazil. Both teams encountered difficulties, with Eddington's Principe site being plagued by clouds and storms, while the Sobral team struggled with equipment difficulties. However, in spite of the atmospheric conditions, Eddington was able to get several good photographs, some of which he immediately sent back to England, while 2 he kept to do an on-site analysis with. The Sobral team also managed to get things working and took a number of clear images. Eddington's early analysis seemed to give a number that was close to Einstein's prediction using the theory of general relativity. However, even as he telegraphed back to Greenwich that his results looked good, he recognized that all of the data would have to be examined before any announcement could be made. And this was a wise precaution. While the 6 images he'd managed to get in Principe as the clouds had parted had indeed confirmed Einstein's number, with a value of 1.61 plus or minus 0.3 arcseconds, the data from Sobral was much more ambiguous. Initially, the data taken from the images made by the primary telescope there only showed a shift to 0.85 arcseconds, much more in line with the case of only special relativity being correct. However, when images taken from a second telescope there at Sobral were analyzed, they agreed more or less with the Principe measurements. Eddington decided that the primary scope must have a flaw that created a systematic distortion of some sort, a view it would take him a good bit of time to prove. Nevertheless, with the Principe data and the second Sobral scope images, he decided to alert the Royal Society of his conclusions. Within days, the news was released to the international media, and on November 10th, the New York Times ran a front-page story on the confirmation that catapulted Einstein and Eddington, at least to a lesser degree, to new heights of fame. In this story, however, there are those who made the justifiable challenge that Eddington, long a believer in Einstein's theory, cherry-picked his data in the form of sort of a confirmation bias. Among them were Lick Observatory astronomers Campbell and Heber. In fact, Campbell had initially planned to finally present his 1918 results contradicting Einstein's predictions at the very Royal Society meeting Eddington was to read his announcement at, but got cold feet at the last minute and withdrew his paper, again due to concerns about the equipment that they had used. It wouldn't be until confirming observations were made from Australia in 1922 by teams from the Lick Observatory, again led by Campbell, the University of Toronto, a group of astronomers from Perth, and Britain's Royal Observatory that provided strong corroborating evidence that the issue was settled for most of the physics community. Though it should be noted that as anti-Semitic rhetoric and ideologies began to take hold in Europe in the mid and late 1920s, there were a number of German scientists who would derisively refer to the theory of relativity, along with the ideas of quantum mechanics as, quote-unquote, Jewish physics. In the astronomical community, the very strangeness of the idea and the difficulties presented by the understanding of the mathematics of general relativity would be a barrier to widespread acceptance and occasional hostility to the ideas throughout the 1920s. With the fuller telling of that story out of the way, I'd now like to turn to the implications of general relativity and where they led. General relativity is actually expressed in a deceptively simple-looking equation. Though, as I tell my students, the simpler an equation looks, the more they should respect it, because hidden down within the equation's simplicity are a number of ideas and concepts that have been folded in that must be fully understood for the expression to make any sense. On the left-hand side of the equal sign in the equation of general relativity is a single term, a space-time tensor or metric, that represents the shape of the fabric of the region being considered. On the right-hand side is a term consisting of a few constants that multiply another tensor that characterizes the distribution of mass and energy that creates the shape described on the left-hand side. The relationship, both simple and horrendously complicated, shows how matter and energy tell space-time how to bend, and how space-time tells energy and matter how to move. Now, like any equation, there are a number of possible solutions to the relationship. A way to understand this idea is to think of a much simpler type of equation. Let's say the equation of a straight line. If I have an equation that's given by the expression y equals 3 times x plus b, there are only certain combinations of x, y, and b that will give a result where the stuff on the left-hand side equals the stuff on the right-hand side. For example, if I choose x to be 2, y to be 6, and b to be 0, then the equation is satisfied, as 6 equals 3 times 2 plus 0. On the other hand, if I choose y equals 9, x equals 4, and b equals 2, that doesn't satisfy the equation, since 3 times 4 plus 2 is 14, and that doesn't equal the y value of 9. In a much more complicated way, the same can be said for Einstein's equation for general relativity. Only certain combinations of the warping of spacetime and the distribution of matter and energy will solve the equation. Einstein's solution for the orbit of Mercury was one such approach, at least in what is known as a second-order approximation. What's interesting is that for this real-world example, the equations were actually too complex to solve exactly, and so Einstein had resorted to a common technique that took successively higher-order approximations to simplify the equation to a workable form. The first-order approximation actually gave Newton's construction of gravitation as the result, thus explaining why Newton's universal law of gravitation had worked so well for so long. The second-order approximation, a process that adds a second set of terms to each of the parts of each of the tensors in the general relativity equation, gave the orbit of Mercury to within observational accuracy, something, by the way, that has been repeated for all of the inner solar system worlds. In February of 1916, another solution was put forward. Karl Schwarzschild, a German mathematical physicist who had been deployed to the Eastern Front, got a copy of Einstein's Berlin lectures and began working with him as a way to distract himself from the horrors of the meat grinder he and his men so often found themselves in. In short order, he produced the first exact solution to the equations, solving them for a point mass located within an otherwise empty spacetime. The common name for such an object today is a black hole, but at the time, Einstein doubted whether such an object could really exist, as Chandrasekhar's work on stellar death was still far in the future. Nevertheless, he read Schwarzschild's paper to the Prussian Academy of Science, where it represented the initial foray into an entirely new field of astrophysics. Tragically, Schwarzschild would never follow up on his groundbreaking work. In a far too familiar story, a few months later, the filth and disease of the battlefield caught up with him, and he contracted a skin infection that would, over the course of 2 agonizing months, kill him. Reaffirmed in his view of the senselessness of this horrible war, and of warfare in general, Einstein gave the eulogy for the loss of such a formidable mind, even as, privately, he raged against Schwarzschild's patriotism that had led him to volunteer for service as an artillery lieutenant at the age of 41. The next step in the development of general relativity was taken by Einstein himself when he published a paper titled Cosmological Considerations Arising from the General Theory of Relativity. This paper was an attempt to resolve a paradox that had been around since the time of Newton. The paradox was, why was it that the mass seen everywhere in the heavens was actually spread out? One of the questions Newton had to grapple with was the reality that if all the mass in the universe attracted all of the other mass in the universe, sooner or later the inexorable force of gravity, the pathological beast, as my old graduate school advisor used to call it, would pull everything together into one huge blob of stuff. Newton had tried to deal with this, somewhat unsatisfactorily, by saying that either things were somehow distributed in such a way as to nullify this outcome, or, as he got older, that God would intervene to restrain the motions of the stars so that they would remain separated. In the first solution, Newton would have had to assume that the universe was infinite in size, with mass distributed throughout, a position at odds with the theological belief that God had created a finite cosmos. Einstein, in his paper, took up this same set of issues when he tried to address, first, the universe's scope. He put forward the idea that the universe was indeed finite, as he couldn't imagine a truly infinite amount of mass. From this, he began to examine the consequences of such a closed universe that would have existed in 4 dimensions. One such consequence was that if the cosmos was contained within some sort of geometry, one could travel around the universe and return to the same point, much as one might do if one were to walk on the equator of the spherical Earth and traverse it all the way around and still arrive back at the same starting point. This, however, opened him up to another problem. If the universe was finite and closed, how did it remain stable? Why didn't it all collapse, both the mass and the energy combined, and the space-time itself? Why didn't that just fold all in on itself? Moreover, given the age of the Earth that geologists were by this time suggesting, how was it that the universe would remain static? It had been clear that the Earth had been orbiting the Sun for over 1 billion years, and, conceivably, the universe seemed to be much the same during that period of time. How do you hold a large number of stars in a void without having them eventually roll across the fabric of space-time towards each other and all end up in the same place? Einstein recognized that a simple equation couldn't produce a solution that led to a long-term stable and static universe. He could get a collapsing universe, and he could perhaps get an expanding one, but not one that remained more or less the same over that long period. As a result of the paradox, he, in his words, committed the greatest cosmological blunder of his career. He added a term to his equation. This term, designated by the symbol lambda and called the cosmological constant, represented the addition of a finite and static amount of energy that exerted an outward, for lack of a better term, pressure on the fabric of spacetime that precisely balanced the tendency of all the matter to attract itself towards a single point. It was an elegant solution to what would turn out to be an unwarranted assumption. At about the same time, there began to be a number of other theoretical physicists, that newest breed of investigators who probed the universe with the pen and paper, who took up the challenge of relativity theory, and the old but now newly reinvigorated field of cosmology, which can be thought of as the study of the origins and nature of the cosmos. Among these hybrids of mathematicians and physicists was the Dutch astronomer Vilem De Sitter. Like Eddington in Britain, De Sitter had been following the development of relativity theory from early on, and he was probably the first to really understand its implications for the field of astronomy. After meeting with Einstein on a number of occasions in 1916 and discussing cosmology, De Sitter began a correspondence with Eddington that led to the man from Leiden writing a series of papers for the monthly notices of the Royal Astronomical Society. The upshot of these papers was twofold. First, they were the means by which most of the world outside of Germany learned of Einstein's work during the Great War. Second, they offered up De Sitter's cosmological solution to Einstein's equation, a solution that was notably different than what the German himself had suggested. Like Schwarzschild had done, De Sitter proposed a very simple model of the universe that led to solvable equations. In this case, a universe that rather strangely had no mass. Now, before you shake your head in disbelief, let's see if I can explain the method behind De Sitter's seemingly absurd approach. One of the things a scientist will sometimes do in considering a complicated system is to think of a simpler system that is a little bit like the complicated system, but that is a whole lot easier to think about. An example we used in one of our earliest episodes of the podcast was an early attempt to understand the motion of the Earth's atmosphere in mathematical terms by imagining a world that didn't rotate, was all covered with water and that didn't have a tilt. While this doesn't much look like the Earth, the model does actually replicate the motion of the Earth's atmosphere at the equator and at the poles. Now, once they had done this, they could sort of take the next step by beginning to relax the simplifying assumptions to see if what they got was closer to the real system that they were trying to understand. Something that has taken place successively over the years in trying to understand the Earth's complicated atmospheric motion. So, in a sense, that's what De Sitter was doing. He was imagining a space-time that didn't have matter in an approximation of a universe where the matter was so sparsely distributed that it was, in terms of the large-scale sense, non-existence. One of the consequences of this was that he got a stable universe. The other was that light, as it traveled across the universe, would have had its wavelength shifted towards the red part of the spectrum. The very results Vesto Slipher had recently presented at the 1917 meeting of the American Astronomical Society regarding the spectra of spiral nebulae. For De Sitter, the observations were not evidence that the nebulae were moving away from the observer at increasing large speeds, but rather that they were further and further away. Eddington, on the other hand, recognized that there was another interpretation of De Sitter's mathematical results, and that was that if a piece of matter was dropped into his static universe, it would move away from some hypothetical center at a speed proportional to its distance from that center. As he said, quote, "Einstein's universe contains matter but no motion, and De Sitter's contains motion but no matter." End quote. While all of this was going on in physics, the various advances in astronomy we've been discussing over the last several episodes were taking place. Shapley had measured the distance to the globular clusters, and in doing so, gotten a more accurate sense of both the Milky Way galaxy's scale as well as moving the Sun far from its center. Slipher had measured the speeds of some 25 or so spiral nebulae, and in 1925, Henry Norris Russell announced Hubble's results confirming the island universe's hypothesis. As had been the case some 8 years earlier, when the young Hubble had sat in the audience where Slipher had presented his data on the radial speeds of the spiral nebula, a young PhD student was in attendance at this most auspicious of moments. Father Georges Lemaitre was at that point studying cosmology at MIT, but his academic career had already spanned nearly a decade and involved the earning of a doctorate degree. Lemaitre had started off in engineering while studying at Belgium's Catholic University of Leuven. As he neared the completion of his degree program, the Great War broke out, and he enlisted in the Belgian army to serve as an artillery officer. Fortunately, for our story, he managed to avoid the fate of men like Schwarzschild, and at war's end, he returned to the university to earn a doctorate in mathematics in 1920 and prepare to be ordained into the Catholic priesthood, something he did in 1923. Following his ordination, he traveled to England for additional study at Cambridge, and while there he met and began working with Arthur Eddington, who recognized his enormous talent both as a mathematician and as a person who could think deeply about the nature of physical systems, a rare combination at the time for those seeking to do work in either relativistic physics or cosmology. While studying at Cambridge, Lemaitre began working with a new solution for Einstein's equation, one that struck an interesting balance between the German's matter with no motion solution and De Sitter's motion with no matter case. In 1925, he traveled to the United States to work first with Harlow Shapley at the Harvard College Observatory and then at MIT, where he began formal efforts towards earning a PhD in physics. It was during this time that he heard the presentation of Hubble's results and realized that his solution of Einstein's equations could very likely describe not just a toy model, but the actual state of the universe, especially if Vesto Slipher's observations of most of those new island universes moving away from the Milky Way could be confirmed and extended. In 1927, he returned to Belgium, and when he did, he wrote Eddington to describe this new model he had developed that not only solved the equation of general relativity, but that also accounted for the observations. He then published this work in a paper titled A Homogeneous Universe of Constant Mass and Growing Radius Accounting for the Radial Velocity of Extragalactic Nebulae. Unfortunately, the journal he published in was little known and not widely read, and so his work went broadly unnoticed by the rest of the scientific community, especially those people working in astronomy. In fact, it wasn't until 3 years later, when Lemaitre heard of Eddington's comments from the meeting of the Royal Astronomical Society, that events finally came together to get his idea out into the scientific community at large. As we mentioned in the intro, by 1930, Eddington had more or less forgotten about Lemaitre's work, begun when he had been a student at Cambridge and continued during his trip to the United States. When the Belgian got word of the conversation, he took up his pen and wrote to his mentor and friend, gently reminding him where to find the solution he sought. Eddington, recognizing his error, reread the paper and in a rush of enthusiasm now recognized it as the breakthrough it was. He immediately wrote to Vilem De Sitter to alert him of Lemaitre's work as an answer to the data that had been gathered in America by Slipher and Hubble. He then sat down to draft an English translation of the work that was reprinted in the March 1931 edition of the monthly notices of the Royal Astronomical Society. So, after all of this introduction, what was it that Lemaitre's paper actually said? In short, the Monsignor had developed an analytically complete solution to the equation of general relativity that described a universe wherein the fabric of space-time itself was expanding, and in doing so, it carried along with it all of the matter of the universe. To understand this idea, there are two pictures that are commonly used as analogies to the process. The first, originally put forward by Eddington himself, is to think of the surface of a balloon that has a number of small pieces of paper glued to it. If the balloon is then slowly inflated to an increasing volume, as its surface stretches and expands, the pieces of paper will move further and further away from each other. The second analogy, which incidentally was the one I initially learned as a young student, is to think of a loaf of raisin bread that is left to rise in the oven. As the dough expands in 3 dimensions, the raisins contained within it will also move with the dough, and thus travel away from each other in such a way that if you happen to be standing on one of the raisins close to you will move the smallest distance away, while those further away will be observed to travel a greater amount, and thus look to be traveling faster. Now, to be both historically accurate and complete, Lemaitre was not actually the first person to develop a solution for Einstein's equations that allowed for a dynamic spacetime that could be expanding. That honor likely goes to the Russian mathematical physicist by the name of Alexander Friedmann, who had written a series of papers back in the period between 1922 and 1924. Friedmann had actually worked as an atmospheric physicist in Russia, serving during the Great War as a sort of meteorologist. After the war, he returned to St. Petersburg, soon to be renamed Leningrad, to work at a geophysical observatory there. While at that observatory, he began to dabble in cosmology as a diversion to his other interests, and before long, he had come up with a solution to the equations of general relativity that combined aspects of both Einstein's static universe with matter and De Sitter's moving universe without it. His model allowed both matter and movement by incorporating time into the equation in such a way that the metrics, as they were known, could evolve. Now, to be clear here, Friedmann's work was very much a theoretical exercise. In the word of Marsha Bartusek, quote, a mathematical enterprise, not astronomy at all, end quote. The papers made no mention of tying the work to any sort of astronomical observations, but rather they can be seen as an attempt to explore the possibilities of what could happen if space-time was temporally dynamic. The results, however, were really intriguing. Friedmann showed that depending on the conditions, space-time could expand, could contract, or could even oscillate between these two states in something he referred to as the periodic world. In one of the papers, he even estimated the age of an expanding space-time to be on the order of 10 billion years, not too far off from the generally accepted number of 13.8 billion that we use today. Though it should be noted that in the same paper, he also said that the age of the universe could be calculated to be infinite, so you got to take it all with a grain of salt. What's missing from his work is any mention of trying to tie the ideas that he's talking about to measurable or observable quantities. Friedman's universes here are mathematical toys, so to speak, with no attempt to connect them to what might be going on in the real universe. Nevertheless, Einstein was familiar with Friedman's work, and, as would become typical of his responses after 1920, he was dubious of its validity. Again, however, tragedy struck an aspiring cosmologist when, in 1925, Friedman contracted typhoid and died a month after making a record-setting ascent in a balloon to make both medical and atmospheric observations. So, to return to the work of Lemaitre, the big thing that distinguished his independent development of these same sorts of ideas from those of Friedman and others doing similar work at the time was that Lemaitre, with his interest in astronomy and physics, understood that his solution offered a chance to really explain what was going on in the observations being made throughout the 1920s. And when I say observations, of course, I mean astronomical observations. Thus, when he published in 1927, he was deliberate in his efforts to demonstrate that the model could account for those actual astronomical observations that had been or were being made. Specifically, he said that in an expanding universe, the galaxies would not travel through space, but instead be carried along with that as space-time expanded at a rate of approximately 625 kilometers per second per megaparsec, a testable number if better observations could be made of galactic velocities. While this is a breathtaking accomplishment when considered through the lens of historical perspective, especially when one realizes that we've not yet discussed Humason's and Hubble's work on the galactic velocity question, which wouldn't be published for another 2 years, it really wasn't widely accepted work. When Lemaitre was invited to the Fifth Solvay Conference in 1927, he had a brief chat with Einstein, who was also in attendance. While the German physicist was more engaged with the questions related to the interpretation of quantum mechanics and the growing debate with Niels Bohr, he did take some time to discuss relativity with Lemaitre. During the conversation, Einstein told the Belgian about Friedman's work, which he had come to reconcile himself with, at least mathematically. His evaluation of both Friedman and Lemaitre's work was rather blunt, however. Quote, "Your calculations are correct, but your physical insight is abominable." End quote. The father of general relativity could not imagine a universe that was expanding. A year later, De Sitter had an equally dismissive attitude towards Lemaitre's ideas. As one writer would later note, quote, "No time for an unassuming theorist without international credentials," end quote. For his part, though, Lemaitre brushed off the criticisms by noting that Einstein was, quote, "not current with the astronomical facts," end quote. These facts would be reinforced and highlighted just a year later. The proof of Lemaitre's model would be forthcoming in 1929, when Milton Humason and Edwin Hubble published a pair of papers that made it clear that the galaxies Hubble had shown were outside of our own were rushing away from us at speeds that increased proportionally the further away they were. This work had begun shortly after the 1926 publication of that paper that fully put forth the island universe evidence, and it involved the recognition that the ideas of general relativity would be an important aspect of that work. Hubble was familiar with De Sitter's work, having sat down with the Dutch astrophysicist at a meeting of the International Astronomical Union. As a result of that conversation, Hubble really began to recognize the need to improve on Slipher's measurements using the power of the 100-inch telescope at Mount Wilson. Given this, Humason and Hubble split the work up in a fairly logical way, with Milton Hubbleson taking the long time exposures of galaxies to get their spectra in order to calculate the spectral redshifts, and Hubble using photographic plates to find either Cepheid variables or nova in the galaxies being studied. From the first set of data, the speed of the galaxy could be calculated, while from the second, the distance could be determined. In a way, this is really a pretty simple idea in the case of, determining both pieces of information for as many galaxies as possible, and then to see if there was a relationship between the two. But, as with so much in experimental and observational science, the hard work was in getting and analyzing the data needed to arrive at that point. Now, to remind you, Vesto Slipher had done much of the redshift determination using his 24-inch telescope from the Mars Hill Observatory in Flagstaff, but the size of his instrument limited him significantly. The 100-inch Hooker telescope, on the other hand, in theory, had the ability to gather 16 times as much light, but the problem that it struggled with was that it was saddled with an inferior spectrometer and photoplate technology. Nevertheless, Humason undertook the job of confirming Slipher's measurements as well as extending them with truly Herculean observing efforts that required him to sit or lay on the telescope's iron frame for hours, guiding its fine controls to make sure it remained centered on the faint smudge of light it was collecting photons from. Together, the two men gathered the needed data and in 1929 published a landmark paper titled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. In this work, we see Hubble at his lawyerly best as he made the case for the idea that the universe was expanding. In his work, he displayed the now famous graph plotting the radial velocities of his galaxies on the vertical axis and the distances to those galaxies on the horizontal axis. The result was that the galaxies fell mostly along a straight line, a line with a slope of about 500 kilometers per second per megaparsec. This number would come to be known first as Hubble's constant and then later as just the Hubble constant, attesting to its importance to the emerging field of cosmology. These results, though Hubble didn't know it at the time of his paper's publication, were exactly what Lemaitre's theory predicted, with even the rate of expansion being close to what Hubble had measured. It wasn't until 1931, however, that with that reprint of the Belgian's paper and the monthly notices, that the world would begin to take real notice. Because of this, there has been, ever since, a misattribution as to who is responsible for discovering the expansion of the universe, with Hubble often being given sole credit. However, as Bartusiak writes, quote, Hubble did not really discover the expanding universe in 1929, as written up in textbooks and commonly presumed these days. That realization did not actually occur until Hubble's data could be viewed with Lemaitre's model firmly in mind. Lemaitre, far more than Friedman, had linked his model with ongoing astronomical observations. His solution was described as a brilliant discovery. End quote. What I think this speaks to, more than anything, is the truth that science is almost always a collaborative effort, wherein many different researchers contribute to a growing body of knowledge that, when the pieces all finally come together, forms a fully coherent picture of physical reality. The work of Humason and Hubble not only provided observational confirmation of Lemaitre's model, its genesis was inspired by the earlier work of De Sitter in cosmology. It very clearly, and when I say it, I mean the work of Humason and Hubble, very clearly used the earlier work of Slipher, an acknowledgement Hubble was a long time in making, by the way, and also the work of Shapley. When the connection between the two pieces of work was finally made, that was done by Eddington, and then, through his republication, recognized by the larger community. As such, the discovery of the expanding universe was the result of a number of efforts carried out by researchers across two continents who, in a relatively short period of time, realized that the cosmos humanity had for so long assumed to be constant was anything but. For many, it would be a hard transition to make. Hubble, by many accounts, struggled with the expanding space-time interpretation of his data, long entertaining other possible solutions to explain the ever-increasing redshifts that he and Humason measured. Einstein, whose resistance to the data was finally overcome after a 1933 visit to Mount Wilson and a series of discussions there, would come to embrace the idea only reluctantly. Yet, for years after, there would be those who rejected even the idea of spacetime as an illusory construct created to explain the observational results. Nevertheless, general relativity, for all of its strangeness, has survived every single test, accurately predicting the outcome of numerous experiments designed to disprove it. So too, the expanding universe. Considered an affront by those who wanted to believe that the cosmos has ever been and will ever be what it is, there has been challenge after challenge to the idea's legitimacy. Still, there is no more successful explanation of the observational data that has been gathered, and so it remains the dominant explanation. However, as you might have already surmised, such an explanation raises a number of additional scientific questions. The most fundamental among these is the question of, if the universe is expanding, what is it expanding from? That, however, is a story for another episode. As I wrap this episode up, please allow me to make a few concluding remarks. As I record this, Hurricane Irma is making its long-anticipated northerly turn to threaten the state of Florida. And, if the forecast models are to be trusted, my home here in central Georgia will be under a tropical storm warning come Monday. My hope is that the necessary utilities and such will survive the upcoming onslaught, and we'll be back with another show in a week's time. However, as is sometimes the case with such things, a lot remains to be seen. To those in Florida riding out the storms, our thoughts and prayers here at the Scientific Odyssey Worldwide headquarters are with you through the fury of the maelstrom and in the recovery afterwards. Remember to trim your sails and keep the bow headed into the waves. The other shout out this week goes to the listeners in Anchorage, Alaska, who tuned in to our discussion of relativity last week in surprisingly large numbers. Welcome aboard the Odyssey, and I hope you enjoy the voyage. I should also take a moment to acknowledge my sources for this week's episode, as they have been vital to getting the story straight. I've already mentioned Marcia Bartusak's The Day We Found the Universe, but please allow me to once again recommend it. It's a really well-written account of the events and personalities that shaped this period. Thomas Levinson's book, The Hunt for Vulcan, has provided much of the material for understanding Einstein's work in general relativity, and it also is a tremendous read. Finally, Ethan Siegel's Beyond the Galaxy has been useful for putting these events in a larger context of what will come afterwards for the development of cosmology. I anticipate we'll be using that for a number of our future episodes. For those looking for excellent sources of reading material on the topics we've discussed here, I would definitely recommend all three. On an administrative note, I'm still gathering opinions on whether I should look to doing a series of biographical episodes on Einstein at the end of our present season. I've heard from a few of you, but I'd really like to get a good bit more feedback. If you'd like to weigh in, you can email me at cldavies@mac.com. Leave a comment at the podcast website, thescientificodyssey.typepad.com, post to our Facebook page, or send me a tweet at Chad Davies. On the topic of biography, I'd like to devote the next couple of episodes to the lives of some of the lesser-known people in our stories, such as Arthur Eddington, Milton Humason, and Vesta Slipher, among others. I'm still working out exactly how I want to do this, but I think shining a light on their work will be both interesting and illuminating. So until next time, full sails on your journey.